All right, well, we're going to get started today. Welcome to our 2014 webinar. I'm Jay Janning, one of the sales engineers in the fan division of Verantis. I'm going to take a moment and introduce the people that I have in the room with me today as support. We have Mary Rusnick, our marketing manager. We have Ralph Edgley, our senior sales engineer. Patrick, our IT guru, to make sure everything runs smoothly. Craig Brackman, also a sales engineer. He represents the Verantis Systems Division and Aftermarket. Mike Gradle, our engineering manager. Worth, our Vice President of Performance Products. The webinar is going to be available in a few days. We're going to send out an email link to it. So if for some reason you don't get the whole presentation, we'll be able to make that available afterward. We're going to keep everybody muted during the presentation. You're welcome to ask questions as we go through the presentation, and I have a few people here that are going to monitor the chat box, and we'll save some time near the end for questions. Also, in the invitation, you might have been aware that we're going to give away a couple prizes today at the end of the webinar, but you must be present for the entire webinar and at the end in order to claim your prizes. So what we're going to discuss today, there's two main parts, and then we're going to leave a little part at the end for question and answers. The first part of this is going to be why FRP, and we're going to compare FRP to metal and different other products out there, and then discuss why Verantis has the best FRP fan on the market. The second portion of this is going to be the do's and don'ts of system design, and courtesy of AMCO, we have a small little video presentation that discusses some of the AMCO standards and recommendations for proper fan performance. So we're gonna start this off here with the different choices of construction and different materials that are available today. We have aluminum fans, which are basically used for air movement, but they offer no protection against strong acids and bases. Carbon steel fans are very common, but often limited in their corrosion resistance. Metal fans, which use a protective coating to provide corrosion resistance, but if the coating's compromised, the fan's in danger of attack. There's plastic fans out there. They're very cheap and inexpensive, but these fans are not usually reinforced, and they're only good for low-pressure applications. Stainless steel fans are okay in certain applications, but bad in others. Depending on the chemical processes, they can also be expensive. And then we have other exotic alloy metals such as hastelloy and titanium. They offer really good corrosion protection, but at what cost? Have you ever priced out the price of an all-titanium fan? And then that leads us to the discussion of FRP. So FRP is fiberglass reinforced plastic. It's a composite material of plastic and fibers used for strength. Some of the more common resins are polyester, or vinyl ester, or epoxy. The glass fibers which are used in industry are a C-glass, which is a chemically resistant, an E-glass, which is an electrical grade, or an S-glass, which is used for aerospace applications. Verantis is standardized on the use of premium vinyl ester resin and the use of a mix of C-glass and E-glass. So what makes FRP so special? The number one reason that people investigate the use of FRP is because the airstream that process is corrosive in nature. This means that using a metal fan or a metal coated fan is not a desirable option because the material of construction is not compatible with the process. FRP is typically less expensive than most alloys, especially hastelloy and titanium. The glass fibers used strengthen the resin and make them an incredibly strong composite. FRP, since it's not metal, is incapable of generating a spark by the material hitting against itself. And whether the fan is moving corrosive air or sitting in a corrosive environment or baking out in the sun all day, FRP fans last longer and are more durable. For example, we have an FRP fan in the New York area that's been running 24/7 for the last 35 years, and they've only had to change out bearings and belts on it. They've taken good care of that fan to keep it running long. So how is FRP fabricated? There's a couple different methods. We kind of highlighted a few of them. The first being hand laid up. This is a process that we use in our impeller department, as well as other parts of our fabrication process. The picture on the right, you can see they're rolling out the mat and the resin in kind of that arc shape, which is used for the impeller blades themselves. And the picture on the right shows them attaching the blades to the back plate. There's also chop spray molding. You can see here that there's a continuous feed of glass, which is chopped in with resin as it's sprayed out the end of the gun. This process is used to fabricate parts that we have molds for, and used for a variety of parts such as belt and shaft guards, inlet bells, some of our fan housings, and transitions. And a couple other ways that FRP is fabricated out there is like vacuum bagging. Usually you'd see this with boat fabrication or large solid pieces of FRP. And there's also injection molding. A lot of different industries out there where FRP can be used. Some of the more common ones are listed here. A wide variety of chemical processes, particularly hydrochloric acid and chlorine salts. Food processing plants. Pulp and paper uses FRP to exhaust chlorine dioxide fumes from paper washers or pulp washers in bleach plants. Metal processing and refining. FRP is one of the best choices out there because of the high concentration of chlorides, where metal alloys only offer limited protection. There's semiconductor manufacturing, pharmaceuticals, mining, particularly salt mines and other mining processes where methane gas needs to be vented out. Rubber and plastic manufacturing, and my favorite, wastewater treatment plants, where they have to exhaust hydrogen sulfide and odor control. So this is kind of a look at what's inside our Verantis FRP. The top picture shows an impeller construction. The bottom shows the housing. Notice that the airstream surface corrosion barrier layers, which is made up of C-bale, 1 ounce of mat, and 2 ounces of chop spray mat. These the structural layers in between will vary depending on the thickness desired. The C-bale may be substituted with Nexus. It offers added corrosion resistance for specific applications. And the exterior of the fan is covered with a top coating which contains a UV inhibitor. This is a list of some of the things that Verantis has settled on as standards in our manufacturing process. The chemically resistant C-bale on all the exterior surfaces. Again, we can substitute this with Nexus. We use a fully FRP encapsulated steel hub. We have one of the fans that truly has no exposed metal in the airstream. Our impeller hub protrudes out of the housing so that no part of the shaft is inside of the housing. Our balancing exceeds industry standards. As I mentioned, we have a UV protective coating on the exterior surfaces. The resins that we choose to use have flame spread rate of 25 or less. We have standardized on oversized bearings and shaft in order to increase life expectancy. We also use 3/16 stainless steel bolting and fasteners, FRP OSHA guarding, and our product is very customizable with reasonable lead times. So all these words are real great, and a picture can speak 1,000 words, right? So as part of our R&D efforts, here are some of the differences that set us apart from the rest of the industry. On the left is a picture of a carbon steel shaft which sat outside and got rained on. Within a couple of months it was completely rusted. Unpainted shafts will start to corrode in as little as 24 hours. On the right is our standard carbon steel shaft, which we paint after assembly, which will greatly extend the service life with reduced corrosion. In the Airstream, the picture on the left here is a shaft permanently bonded to the hub and then encapsulated in FRP, but they neglected to coat the entire shaft, which will come in contact with the Airstream. On the right is a picture of our fully encapsulated hub, which protrudes out of the housing in order to comply with the requirement there's no exposed metal in the Airstream. Air bubbles. Air bubbles will reduce the strength of FRP, but most importantly, they may seriously affect the corrosion resistance. According to ASTM C 582, there are standards on entrapped air bubble sizes and quantities per area. The picture on the left violates both of them. And for those, the picture on the right is our picture of our FRP, our clear. And for those of you who think that I just picked a small section of the good and the bad, this is a picture of what we cropped in order to show that. So you can get a bigger idea of, 10 inches on each side on what the FRP looks like. Uniformity of construction. Our competitor on the left there, it shows irregular surfaces that can cause uneven buildup of contaminants, increased vibration and instability. It can also compromise the integrity and the strength of the impeller. On the right is our impeller, which stays in balance for longer periods of time and is not subject to the same problems that our competitor has. Now in balancing, we always add weight to our impellers when balancing. Adding dissimilar material, as shown on our competitor's fan on the left, can be prone to delamination and can result in unevenness and problems when balancing. And if you look there on the, let me get my little pointer out here, you can look right here, you can see this is already starting to flake up a little bit, which is going to be subject to attack. On the right is our impeller, which stays in balance for a longer period. On the right is our impeller. But what we do is when we add weight, we add the same material, the same chop mat and resin that the impeller is made out of. It's really hard to see, but this right here is where we've added the weight into the impeller, and it's seamless. Now, this is what happens when you remove weight. And like I said, we don't ever remove weight. We only add weight for balancing. The impeller on the left, they actually ground the inside of the impeller in order to balance it. And then they neglected to re-top coat it. So what you're looking at, those white spots right there, are actually exposed fibers, which are going to be prone to chemical attack. Also, we'll discuss this in a little bit, but this picture on the right, the inside there, let me see if I can get my little red dot back out. This right here is a giant air bubble that was formed, and you can see some more air bubbles right here and this area in here. And it is a little hard to see in this picture, but there's actually cracks that run right down here at the seam where the backplate and the impeller were attached to each other. These fans also, these pictures that were taken were of unused fans. So this hasn't seen any chemicals or run. On the right-hand side here, you can see where they took this plastic impeller and they ground it down. That's going to basically lead to unevenness and ultimately to an imbalance of the impeller. Now, clear resin, sometimes projects require that no pigments, dyes, or colors be added to the resin. Both of these pictures are examples of clear resin impellers. The competitor on the right-hand side, on the left-hand side, the resin and the FRP was set up too fast, and it isn't actually colored, it's actually burnt because it overheated. You can see the excessively large air bubbles. This is the same impeller I showed just previously. You can see the air bubbles that have started to form right here. That term is actually crazing. And crazing is heat-induced stress fracturing. On the right is an example of one of our clear resin impellers. You can actually stand there with a light and shine a light through it to inspect for imperfections. Not that you'll find any. So delamination of FRP on plastic. The left is an example of one of our competitors that fabricated a plastic fan and then overlaid it with FRP in order to market this as an FRP fan. It's very difficult to achieve a strong bond between two different materials, and as you can see, there's a little crack right here and there's one right here where the FRP is already starting to pull away from the plastic. Again, these haven't been used or run in a contaminated area, but that's certainly some points for attack right there. On the right-hand side, you'll see the smooth consistency of the inside of our housing, which is attributed to the C-bale layer. All right, now a baffle box is essentially a dam that's inside of the fan that's used to recirculate the air, to reduce the swirl at the outlet, also to help increase the static pressure, particularly on backward inclined impellers. The left side looks like they added and glued in a paint tray and then bolted it to the side of the housing. You can see the glue right up here that's attached, and they put another little patch of glue right here, and then they bolted it. And this is in the airstream, so along with the shaft that was exposed, they also have a metal bolt right here that's exposed to the airstream. If the airstream is corrosive at all, that bolt is going to eventually come off, which means that their little baffle box here is going to come off and fall right into the impeller. On the right-hand side, you'll see our version of a baffle box. You can see that we've made this pretty sturdy, really solid, and it's an integral part of the housing itself. All right, now we have a little 5-minute video presentation from AMCA that's going to discuss system effects and designs. We were going to put together something ourselves on system effects and designs and our recommendations, but I don't know if anybody could say it better than AMCA could. So let me get this video started. Like I said, it's only about 5 minutes long.
System effects can be described as fan performance loss, the detrimental effect on fan air performance due to adverse flow conditions at both the fan inlet and the fan outlet. In addition to adversely affecting fan performance, system effects can also increase noise, increase vibration, and cause premature impeller or bearing failure. When designing buildings and air systems, minimizing energy use is of the utmost importance. the emphasis must be on eliminating system effects, rather than simply identifying and accounting for them. Quantification of system effect is necessary to evaluate improvements to existing buildings. For optimum system performance, the airflow at the inlet must be fully developed, symmetrical, and free from swirl. Ducting on the outlet needs to be designed so that the asymmetrical flow profile from the fan is allowed to diffuse and approach fully developed flow. The effect on fan performance when these conditions are not met is called system effect. You can master all the theories about how to design and specify systems to move and control air efficiently, but until you actually build and install the components, you won't really be able to understand how seemingly small changes in execution and installation can have a dramatic impact on the performance of the system. Therefore, it is important to understand system effect because of the significant impact it has on the efficiency and operating cost of the systems you design and build. System effect at the fan inlet and outlet seriously impacts airflow. The first major impact involves proper fan inlet design. As stated earlier, the airflow at the inlet must be fully developed, symmetrical, and free from swirl. Non-uniform inlet flow is the biggest cause of system loss. Factors adversely affecting inlet flow are insertion of obstructions, elbows and dampers too close to the fan inlet. Let's assume we use an open inlet as a benchmark, with the inlet velocity set to 1 inch of water velocity pressure. If we affix a poorly designed right angle inlet box directly to the inlet side of the fan, our velocity pressure is reduced to just 0.6 of an inch water, a 40% reduction, which equates to a 23% loss of airflow. If we improve the design by adding turning vanes to the inlet box, we improve the velocity pressure to 3/4 of an inch water, but that's still a 13% loss of airflow. Changing the inlet box to an elbow will help. Properly installed, a sweeping radius elbow will result in only a 3% loss of airflow. A good rule of thumb is that elbows near the fan's inlet should be radiused and include turning vanes when located within 3 duct diameters upstream of the fan, recognizing that mitered elbows with or without turning vanes can cause system effect even when located up to 5 duct diameters upstream. The second major impact involves proper fan outlet design. The same elements that have an impact on inlet design, namely ductwork and dampers, also have an impact on outlet flow. Let's assume 1 inch water velocity pressure on the outlet side of a fan, similar to the inlet side in the example just given. If we add a right angle elbow on the outlet side in the direction of the fan's rotation, we reduce the velocity pressure to 0.85 of an inch water velocity pressure, which is an 8% loss of airflow. However, if we change the direction of the elbow to opposite that of the fan's rotation, we reduce it even more to 0.7 of an inch of water velocity pressure, which is a 16% decrease in airflow. So major ducting inefficiencies can occur on both sides of the fan. One must also remember that a major additional factor is the length of the ductwork itself. You should always strive to achieve 100% effective duct length. Ducting on the outlet needs to be designed so that the asymmetrical flow profile from the fan is allowed to diffuse and approach fully developed flow. The point where this is achieved is referred to as 100% effective duct length. A good rule of thumb is that effective duct length is 2.5 duct diameters when duct velocity is 2,500 feet per minute or less, with 1 duct diameter added for each additional 1,000 feet per minute. Testing in the AMCA lab has shown that a centrifugal fan needs 100% of effective duct length to avoid system effect, while a vane axial fan needs 50% effective duct length. So remember that in a ducted inlet, ducted outlet installation, system effect may occur on both sides of the fan. What is so striking
All right, so there's our little video presentation from AMCA. And there'll be a note later on after this, but this video and like I said, the webinar itself will be available afterward if you need to rewatch the video and take notes. So talking about system design and effects, this is sent from a recent customer who put 2 of our AMCA certified fans into their system to pull air from the tank vessels that you see on the left. And then they called me up and asked if I could help them to explain why it was they weren't getting the flow and pressure that they needed or expected. The first question that they asked me was, why isn't your fan working properly? After a little bit of research, I asked them to check the motors to make sure they were wired properly. I know that seems a little funny, but they called me back the next day and said, yep, we wired the motors backwards. These were backward inclined impellers, so that alone made a significant difference. Then we started to discuss the areas in their system where they might have unaccounted for some losses. So I highlighted here with the little yellow circles all the different areas where they might have not accounted for losses that they might be experiencing. To start with, they were measuring the inlet flow and pressure over here off this nozzle. And they were measuring the outlet about 7 feet up this pipe on the stack here. So we had a lot of back and forth and some involvement with engineering as to how we can kind of help them correct this. One of the first things that we talked to them about when we cited AMCA was that they needed to have the proper duct length feeding into the fan for the proper airflow. The inlet right here on the left-hand side was basically a 90-degree right into the fan. I also got a picture on the right of the valves that they chose to use, which obviously you can see is a huge obstruction in the airflow. Without getting too critical of their design, since the gentleman that I was talking to was the man who designed the system, as I said, we kind of cited AMCA and talked about proper duct length. So they made some changes, and then they sent me some feedback of what they had changed. And as you can see, they added some straight ductwork into the fan at the inlet in order to get that properly developed flow. But what the result here was, or what they ended up doing, was adding in 2 45 elbows right above the inlet in order to get this pipe a little further away. And what they gained in the straight run, they lost by adding in more bends before the inlet of the fan. We are still currently working with them to help them resolve this issue. Another example that was sent to me here, we refer to this as the fan centipede. And I'm not really sure where to begin with this one, but this was the picture that they sent over to me on their system and wondered if we could help them figure out why they weren't getting what they thought they would. To start with, the arrows that they gave us in this picture are actually pointing the wrong way. So the first correction that we made, and I'll show you in the slide here, was to correct the proper airflow. I believe that the intent here was to boost the pressure, but each one of the fans is still subject to the same fan laws and recommendations by AMCA. We have an outlet right to an inlet, and then an outlet right to an inlet, and then right after this final outlet, it's hard to see in this picture, but it actually goes into a 90-degree bend and straight up. Again, this is a real tough one to even know how to address. So that wraps up the presentation portion of this, and I'm going to open up the chat box here and see if we have any questions that we can address. Should I answer that question? All right, so I have one question from Jack Shelton. Jack wants to know if he won. Jack, my answer to that question is I think that you win just by being here and taking in a little knowledge of the product. Are there any other questions that are out there?
Oh, yeah.
Oh, we did actually have a question that came in right before the webinar started. They had asked why we use carbon fiber, or why we use glass fibers instead of carbon fibers.
Basically, the short answer to that question is cost. In order to get the performance out of carbon fiber, you have to get the fiber ratios real high, which takes some very expensive both vacuum bagging and autoclaving, and that's pretty much why you see it in aerospace, not in applications like this, or it's just cosmetic. You see the carbon fiber, but the fiber ratio is so low you don't get much of the benefit. So there's times when you'll see it and it looks nice, but
sorry, Mark, that was Mike Gradle, our engineering manager, who handled that question. How does FRP construction compare in cost to stainless steel? From our research, we're competitive, if not cheaper, than most of the stainless steel products that are out there.
One of the advantages that the stainless steel would have is if you're going to really high statics. This is Jeff Ward speaking. The housings and the impeller and the construction sometimes a little more expensive than the FRP, but a lot of times not as much service life because of the FRP's, advantage to a mix of things that it's better for corrosion protection. One of the things that was really important for us was actually looking at our product versus our competitive products, and those pictures are just a little sampling of some of the differences, or what we call the Verantis advantage. We find ourselves as a company price competitive with them, but far superior with our competitors in quality and longevity. So there's really a cost advantage when doing direct comparisons, and the quality advantage is readily apparent to the layman. It's just that most people don't get to see the insides of the fans because of the contractors and the system designers and everything. The end user only gets to see an installed system.
Thank you, Jack. Jack says best FRP fan in the business.
well, it's actually I see the what is the smoke rating. I think that would be flame spread rating, which is less than 25 for our fire retardant, which is standard housing resin.
We have a question on the kind of paint we do on the shaft. It's the same that type A finish. It is, which is what's type A, polyurethane paint? Yeah, it's a polyurethane. There are different levels that we can do, all the way up to powder coating or galvanized. We do some stainless steel bases. We do stainless steel shafts. We do titanium, Hastelloy, Inconel, depending on different applications. So quite a variety. That's one of another advantage to a Verantis product is the customizing or the special applications. That's where we really stand out as well.
Maximum operating temperature for FRP construction.
Well, Ray asked again what he said. That's the flame rating. What's the smoke rating?
There is a smoke rating. I don't know that.
Yeah, I don't know.
Isn't it that coating that intumescent?
Intumescent.
Yeah.
There is a like a top coat. I'm going to slaughter this word, but I believe it's intumescent. That gives reduces the smoke if it were to burn. That is an option. Again, with our customizable options, we can add that coating onto the top to give it an extra smoke rating.
So question, what is maximum operating temperature for FRP construction?
With the high temp resin, typically 250
Fahrenheit.
Fahrenheit. Yeah, not centigrade.
Standard shaft carbon steel.
Yes.
Yeah, the standard is a carbon steel shaft, which we paint all our carbon steel shafts for the added protection. Just one of those extra steps that we take. And one of the other ones that Jay mentioned is that all our hardware on a standard fan is 316 stainless steel. We don't use carbon steel bolts, or in some special applications we might use titanium Hastelloy or Teflon coated, depending on whatever the request is.
Ray, I don't have that information in front of me. As I'm sorry, Ray is asking what is the rating, the smoke rating, and if what's the standard and optional. I can get that information definitely. I don't have that information in front of me right now, so I'll contact you. We have another question too on, do we have graphite impregnation option? Absolutely. We, if you ever need spark resistance, the graphite impregnating, we have a carbon gel that we will coat the impeller and the inside of the housing. Basically anything that comes in contact with the airstream, we can coat it with a carbon gel for that.
Then we can also make the FRP using graphite impregnated resin and or graphite glass instead of the fiberglass. So we've done that as well.
Does Verantis employ any type of labyrinth type seals? Yes, we do. We actually didn't even discuss shaft seals, but we can do Teflon, Viton, or neoprene. We manufacture an FRP stuffing box. We can also provide mechanical seals, John Crane or Chesterton seals. The John Crane, we can do those single, double, with an air purge. Certainly the labyrinth type seals, we have like a double Teflon or even a triple Teflon type seal that will meet those requirements.
Well, if there's, we just got a question from Jack. Sound is always important. One of the things you'll note, Jack Shelton has a question about sound is always important, or a statement. And one of the advantages to us is our fans are generally quieter than our competitors, and I think it's because of the robust designs and standards. We're a little thicker, a little bigger, a little heavier than our competitors. We exceed all the industry standards for balancing. So the old guys talk about a nickel test where they stand a nickel on end on a running fan, and it doesn't tip over. So I think there's, everybody's motor is the same, but I think our fan is different. It's better. So.
And Jack, I've handled a lot of specifications, particularly in the wastewater, where they call out certain decibel levels at a certain distance from either the property line or 3 feet or 5 feet. I can only think of a few examples where we didn't meet or exceed, where we did not meet or exceed the sound requirements. Like Jeff just said, typically our fans are a lot quieter than our competition.
And in the cases that we didn't meet or exceed, we didn't know the requirements.
Can you give a list of all the questions?
One thing that we would like to open up to everybody is that we're very proud of the product we make, and we'd love to have visitors out at our facility so people can see firsthand, what it is that we do and why we're different and why we're better than our competitors. So it's an open invitation to any customers and reps and anybody that wants to come and visit us.
Come enjoy the Cleveland sunshine. All right, so we're gonna close up the questions. I'm gonna give an email right at the end of this if you need additional information.
I believe Mary's doing the drawing, right?
Yep, and the last portion of this, we have our winners. Andy Stivora and Ray Pasquinelli are our two winners today. Andy and Ray, we're going to contact you after this, either by phone or by email. You have a choice of your prize, so we'll contact you and we'll discuss that. And finally, we'd just like to say thank you for coming and being part of our webinar. As I mentioned at the beginning, this has been recorded, so we'll have it available. We're looking at putting it up on YouTube so it's accessible. You can also visit Verantis.com to see our product line and more information. And if you have any questions for us, they can be sent to info@verantis.com. And I'd just like to say thank you, everybody, for attending.